I wanted to take a little time to try to give you some background on this thing, the natural base E. Um, E itself is a constant, and on many calculators, especially scientific calculators, they have an E button, and that E button gives you 2.718 da 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 da, a bunch of other numbers. E is an irrational number like pi, and it's a constant like pi, and constant means it's always this number. So whenever you see E in formulas, certainly in this math class, this E means approximately 2.718, and that's it. We'll use it in conjunction with variables like x, but don't be fooled. E is still just a number, and it's the same number every time. Now, I want to give you a little bit of a background. There's a formula for calculating interest, or compound interest, on money. If you put money into, like a bank, we would call P the principal, the money that you initially deposit, and you get a certain amount of interest, R, the interest rate, and that money is compounded over time. In other words, maybe the interest is paid annually, or maybe it's paid every month, or maybe it's paid quarterly, or maybe it's paid every day. And down here, this n, if we have annual compounded interest, that n is 1. And if we have quarterly compounded interest, that n is 4. And if we have monthly compounded interest, that n would be 12. And this n is the same as that n. So anyways, this is kind of how the formula works. If we put in $1,000 for P, and we got paid 5% interest, 0.05 would go here. And if it was compounded monthly, we'd put 12 here and 12 here. And then we'd put the number of years. And then over here, we could then calculate what we would expect to get if we had this amount of money earning this amount of interest. So that's the compound interest formula. I want you to notice that down here is a formula that looks an awful lot like it. We've got 1 plus 1 over x raised to the power of x. And it turns out some smart folks a long time ago figured out that if you have a formula that looks like this, and you increase the value of x here and here, and you keep making x bigger and bigger, so here's x where it's 10, and then 100, and 1,000, 10,000, 100,000, and 1,000,000, what happens is the value of this guy right here starts to approach a specific number, and that specific number is 2.718 da 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 da, also known as E. So the bigger the value of x gets, the more decimal places that we get for E. Sort of like maybe you've heard that for pi, they're always working on trying to get more decimal places for pi by computing it. So anyways, down here it says the natural base E is irrational, and if you take this formula as x approaches positive infinity, E becomes approximately this number here. Okay, so that's a little bit of background on where E comes from, but I want to give you a sense of why we care about E. All right, I found this neat web page. It's called betterexplain.com. And there was this particular article that says it's an intuitive guide to exponential functions and E. So as I was looking at this, I thought they had a pretty good explanation of what's going on with E. They say that E is not just a number. Describing E as a constant is like calling pi an irrational number approximately equal to da 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 da. Pi is the ratio between the circumference of a circle and the diameter of a circle, and that's true for all circles. So pi is a pretty big deal in addition to being this number. And it turns out that the same is true for E. E is known as the base rate of growth shared by all continually growing processes. In other words, E lets you take a simple growth rate where all change happens at the end of the year and find the impact of compound continuous growth where every nanosecond or faster you are growing just a little bit. So, in other words, what they're saying is that E can help us to compute something called continuous compounding. Up here we talked about compound interest, and I said to you that you could have a compounding of every quarter or every month, but I forgot to mention you could compound every day, or you could compound and by the way, every day N would be 365. You could compound every hour, or you could compound every minute or every second or every nanosecond. And if you could compound continuously, in other words, all the time, then we no longer have a formula like this. Our formula magically turns into this: P times E raised to the power of R times T. And this is the formula for continuous compounding. So that's kind of an exciting thing, is that if we wanted to calculate the best possible case for compounding interest, continuous compounding would be it. And again, we put in E because E is what you get when you take something that looks an awful lot like compound interest, and you take this value N and you make it into a bigger and bigger number. Okay, so there's another aspect to E that I want to share with you. So in accordance with what we just read, if E is the natural growth rate for things that occur naturally, then it would make sense when we have this formula. You might recall the one that looked a bit like this. In this case, I'm going to do it as a decay, 1 minus r to the power of t. If E is a natural representative for growth or decay, then maybe we can replace this formula for now, not always, but when we have something that's naturally growing or decaying, we can replace it with this formula, where we have y equals a times e to the whatever. I'm going to tell you there's a version of this formula for decay and for growth. If you'd like, you can pause and write the two down. And in these formulas, the A is still the initial amount of stuff, and the Y is the amount that you eventually get. The X could be a T, and the T obviously could be time, and so this Y would be the amount of stuff that you have after a certain amount of time has passed. And the R, again, has to do with the growth rate. And over here, if we have a negative R, then the negative R would actually be the decay rate. And again, the X could be T, and the A is the initial amount, and the Y is the amount you get after a certain amount of time. Now, one of the usual applications for a formula like this, the decay formula at least, is for radioactive decay. It's hugely important. One of the reasons about how we know about how old the Earth is, and how old bones are, and how long man has been around, and all of these different things, a lot of it has to do with radioactive decay. Maybe you've heard of carbon-14 dating. Well, there's other kinds of radioactive dating that lets us determine how old rocks are on Earth. So anyways, this formula, it helps us to determine if we know the initial amount of a particular substance, we can use E as a sort of our growth or decay rate for natural substances, and then we use this R to sort of tweak this value over here. And then we put in an amount of time, we could figure out how much we expect to have at the end. And of course, for radioactive decay, maybe what we do is we say, this is how much we have now, and we'd like to know how much we had at the beginning, possibly. Or, this is how much we suspect we had at the beginning, this is how much we have now, and therefore, how much time has elapsed in order for that to happen. So anyways, I just wanted to give you some overview about how this formula is used, why there's an E in it, and how we can get growth, it's when R is positive, and how we can get decay, it's when R is negative. Just wanted to give you a quick intro to the idea that we can use these formulas. And again, the reason why we use E is because if we have an element that is undergoing radioactive decay, it's undergoing constant radioactive decay. So what happens is that when you have a substance like uranium or whatever your radioactive material is that if it is constantly decaying, another way to say that is it's continuous decay. And that kind of relates back to the formula that we had earlier for continuous compounding that had the E in it. So if we have continuous decay, using E as our constant makes a lot of sense.